Hi, my name is Matt Weber with cbec Eco Engineering. The Sacramento, California area is one of the most flood risk metropolitan areas in the United States. Today I'll be describing an effort that we conducted to evaluate existing revetment on the Lower American and Lower Sacramento rivers in Northern California. To begin, I'll discuss the location of the effort, the need for the field data and assessment of the existing revetment sites. I'll describe our scope of work and methods, and lastly, discuss the preliminary results. The bank and levees that were assessed include the Lower American River levees within Sacramento County, which is the lower 14 miles on the right bank and 12 miles on the left bank, and the Sacramento River East levee, which is a 15-mile contiguous levee from around the American River confluence down to the Freeport, California. For some historical context on the need for this flood protection infrastructure, the Sacramento area is one of the most flood risk areas in the nation, as I said before. There are mega floods in the paleo record. A large flood occurred in 1862, which is shown in the photo on the right. That's actually downtown Sacramento. Recent large floods in 1986 and 1997 have caused over billions of dollars in flood damages. And the U.S. Army Corps of Engineers has identified an urgent need to modernize flood infrastructure and provide a greater level of protection against catastrophic flood events. So currently, this effort began after the Bipartisan Budget Act of 2018 was passed. This created the authorization and the funding for the Army Corps of Engineers to start assessing and implementing bank protection designs, as well as other flood infrastructure improvements in the greater Sacramento area. And in order to carry out that project, it's needed the need to determine if the existing revetment provides adequate protection is necessary in order to prioritize and rank sites that need to be treated with new bank protection designs. At some of these existing revetment sites, there's limited data, such as no design reports, specifications, or design services. So in those situations, this field work is really necessary in order to have any kind of assessment on the current conditions and whether or not that site meets modern design standards. In addition, the Lower American River, the erosion repair sites there were primarily designed for a flow of 115,000 CFS, whereas the current design peak flow for the Lower American River is 160,000 CFS. So it's necessary to revisit those sites and check against the new design flow standard of 160,000 CFS. Lastly, one of the huge needs for doing this work is that there's a large benefit to limiting the extent of new bank protection work. So as existing sites can be determined that they provide adequate protection, then we can reduce the extent of new bank protection work, which lowers costs, lowers scheduling and environmental impacts, and lowers the need for off-site mitigation. For our scope of work, it comes in 3 components. The first component was a desktop review in order to determine the sites that needed to be assessed. We assessed all modern designed angular riprap sites within these 2 areas described before, the Lower American and the Sacramento River East levee. In addition, a subset of historic sites that were identified in collaboration with the Sacramento Area Flood Control Agency and the Army Corps of Engineers. And then for these sites that were identified, we compiled and reviewed existing design documentation and evaluation reports in order to document the design specifics, as-built conditions, and past evaluation reports on their conditions. For field work, we included a above water riprap assessment, which involves visiting the site and delineating the upstream, downstream, and upslope riprap extent and riprap types. So for different riprap types, those edges of those different riprap types were delineated, including subsurface riprap that was buried with a soil layer, which was determined with the use of a soil probe. And during this process, we're also GPS tagging the slopes and extents and providing photo documentation. In addition to the extent delineation, we perform representative transect surveys in order to characterize the site. So depending on the complexity of a site, there may only be one representative transect, but some could have as many as 3 to 5, depending on how the design changes along the length of the site, or how different revetment conditions change throughout the site. Within one of those transect surveys, we collect a 100 rock Woolman rock count with 3-axis length measurements, which I'll describe more later. Perform 3 thickness measurements per transect to determine the thickness of the revetment. 3 rock samples are collected for density measurements to make sure that the rocks are of adequate density. And then lastly, GPS and photo documentation is also compiled. For the below water riprap assessment, we collected multi-beam and side scan sonar, both of which are surface techniques in order to delineate the below water but surface extent of the riprap. And then we also collected sub-bottom profile surveys, which include a different sonar frequency that is able to penetrate sands and muds, and that can map out the buried extent of riprap. Combined, those data sources allow us to determine the below water riprap coverage, slopes, and elevations, and most importantly, to assess current toe rock volumes for launchable rock checks, launchable rock adequacy checks. So the assessment criteria that we're using to compare all this field data to is the Army Corps of Engineers Manual EN 1601, which is the hydraulic design of flood control channels. And within this document, there's riprap design criteria given for riprap slopes, the D30 size, gradation, shape, density, thickness, coverage extent, and launchable toe volumes. So in this methodology, we conduct we capture the field data necessary to calculate these different values and check them against the design criteria using a modern HEC-RAS 2D model with updated bathymetry and roughness assumptions. Here's just a quick overview of the sites, just to get an understanding of the spatial extent and number of sites. So this is the lower end of the Lower American River, and the sites here are largely bank repair sites that were built post flood erosion after certain events like the 1986, 1997 event, etc. Here's a view of the sites on the upper portion of the Lower American River, and then the upper portion of the Sacramento River East Levee, and the lower portion of the Sacramento River East Levee. So collectively, this is 43 sites with approximately 7.5 river miles in length. For the above water field work, we go out to the site and, as I said before, use a soil probe and RTK GPS to delineate the different rock types and extents. So in this site, there's different upper and lower bank angular riprap. The upper angular riprap is not contiguous along the site. It was placed along localized erosion sites along the upper bank. And then there's a subsurface cobble bench that includes vegetation that was designed to be planted within the cobble bench, and then an angular riprap lower bank. So that gets delineated, and then depending on the complexity of the site, as I was saying, we conduct different transects to capture the differences in design elements across the site. So for this site, we have 3 transects, and each transect will have thickness measurements and Woolman rock counts for each rock type that is encountered. And by rock type, I mean a particular set of revetment that has a defined gradation. So in this case, the lower bank has one defined gradation, and the upper bank has another defined gradation, and the cobble has another defined gradation. So for this site, there's 3 rock types. Along the way, we're also providing photo and GPS documentation to provide in the report. For the below water field work, the multi-beam and side scan sonar was captured across the entire site in order to provide elevation data and slope data, as well as use the high resolution nature of the data to map out the extent of the surface riprap. So with sonar, side scan sonar, you can use the intensity of the return to map out the surface revetment. In addition, with the multi-beam, if the resolution is high enough, such as in this top image, you can really just look at the textures and the standard deviation of the nearby points to see how the roughness is showing the riprap along the bank and then the sands in the channel bed. So combined, this gives us our surface coverage plus elevation and slope data. The sub-bottom profiler survey includes 50-foot transects that are perpendicular to the bank. So this is a lower resolution survey, but it can provide subsurface coverage of the riprap. So the frequencies of sound waves that are used are able to penetrate muds and to a lesser degree sands, but can penetrate sands and get different signals based on the composition of the subsurface material. And that lower image shows some sub-bottom transect where the blue is contiguous angular riprap. Here's a look at laying out the idealized sub-bottom profiler surveys and a view of the setup where a towfish is attached to the survey vessel in order to conduct the transects. While we're doing the sub-bottom profiler surveys, and I'll spend a little more time on this than the other surveys since it's maybe less familiar to us all, but the sub-bottom profiler survey requires interpretation of the signals in order to delineate what is riprap or what is sand in this case. So it's really important while doing these surveys to have a way of validating the signatures. So while we're out surveying, we're using probes and visual confirmation if the water is clear enough to see the bottom while we're doing a transect. And then this is a live stream image of the sub-bottom profiler data where we're taking screen captures of different points and annotating that we confirm that there's rock signatures at each of those locations, either visually or with a probe. And during that process, we can see the signature that we're getting from the riprap and compare that to the signature that we're getting when we move into the sand channel bottom. So in this case, we're seeing a relatively large but mottled texture along the revetment or the riprap, and you can see that plunges a bit below the subsurface of the consistent fine-grained but harder returned on the sand surface. And here's another look at that. There's a rock hump here with riprap, and then the sand, the consistent sand signature of the channel bottom. when we look at the data in the post-processing software, we're able to look at different gain settings and provide a finer resolution look at that data in order to delineate the riprap extent. So these two images are using two different softwares, but on the left and right image is actually the same transect with different XY aspect ratios. But we can see that there's revetment contiguous along the slope, and it extends some distance beyond the present day toe due to sand deposits essentially being deposited here and burying some of the pre-existing installed riprap. You can see that same signature here. So the wiggles here are delineating the riprap, and then you can see the very fine but consistent sand sub-bottom or subsurface delineation here, and the revetment extends slightly beyond that. So with this data, we're able to look at the riprap and note that it's contiguous all along the bank. There are no pockets of launching material that has reduced its thickness or slope breaks that may indicate some prior event that manipulated this sloped surface. And we use that information in order to, one, map out the extent, but also to provide an assessment on whether or not the as-built information is still valid. And if the as-built information is still valid, then we can use those as-builts to calculate the existing toe volume that is available for launching. So lastly, here's just one more transect where you can see the plan view and the profile view. So this site is being shown in the pink line here, and you can see the consistent riprap signature, and it extends below the below the bottom of the channel to approximately this extent here. So that's the value of the sub-bottom profile. It's really giving you that signature. You can see a relative thickness, the contiguous nature of the protection along the lower bank, and you can see that this lower bank has a consistent slope down to the toe. There's no pocket of material that's absent or a slope break or a signature down here at the toe that would indicate that material has launched. So once we have all these data sources, we have extents that were delineated from the above water field data. We have the multi-beam that's giving us slopes and elevations and surface extent. And then we have the sub-bottom data that's able to delineate a little further into the toe to see if there's buried riprap. We can then delineate the total extent of the modern bank protection site or the historic site, if that's the one that we're analyzing. And this is then used to validate that as-built information is still correct for present day, as well as feed into the locations that are used for depth and velocity outputs from our 2D modeling to use for the riprap size calculations. So here's just another viewpoint showing the extent of riprap for this modern bank protection site. Some of them are rather small repair fixes. And then you also note that there's toe rock delineated by these blue dots that are not associated with this site. So the Sacramento River has historic rock pretty much along the entire length of both banks. So there's a subset of this bank that is the modern revetment site, which you can see pretty clearly with the change in the DEM colors here. But then we're also picking up some historic rock that is likely buried in these sands from the sub-bottom profiler signal. Here's another site with an interesting surface signature that really showcases the value of the sub-bottom data, where we can see there's contiguous lower bank rock down to this toe right here. But then we have these humps of texture that appears to be riprap that was likely placed there from the barge. But it appears that there might be sands in between those humps. And so the sub-bottom data is then able to decipher whether or not there is subsurface riprap that is contiguous with this lower bank toe out to the edge of these riprap humps that we're seeing, or if this is actually the end of the contiguous toe of riprap. And so for this site, actually, we're able to see that the riprap does extend all the way out to here, and the sub-bottom then is capturing additional material that wouldn't be captured if we were just looking at the surface returns from the multi-beam and the side scan sonar. Lastly, after the bathymetric rock evaluation data was collected, we use that to make a determination if the as-built information adequately captures present-day conditions. If so, we're able to use those as-built drawings to digitize and delineate the cross-sections to estimate tow rock launch volumes. And for this, we're using scour calculations that were provided by Northwest Hydraulic Consultants, and then using the EM 1601 section 3-11 equations to estimate launchable rock volumes that are necessary given a particular scour depth and design thickness. Then we can compare that to our measured or estimated tow launchable rock volumes. Finally, with the riprap gradation, slope, thickness, and size measurements, we then use equation 3-3 in EM 1601 to reorient this equation in order to solve for the riprap safety factor. So equation 3-3 is usually set up to solve for the D30, so the 30th percentile of the riprap material, where 30% is finer by weight, and it's a length measurement, such as, in this case, we have 0.67 feet is the D30. So the typical equation is set up to solve for the D30, but in this case, since we're evaluating existing riprap, we know what the D30 is because we went out in the field and measured it. So we reorganize the equation in order to solve for the safety factor. So the safety factor is something that's within the equation in order to provide the level of factor of safety. So in this case, we're calculating that safety factor, and then the Army Corps of Engineers can use that information to determine if the safety factor is high enough to meet their current level of protection. And so this site is just showing our input values that come from our field data, and then we're checking the safety factors under a different combination of flow scenarios from a HEC-RAS 2D model in order to have a sensitivity analysis on this factor of safety. When all is said and done, our output can be summarized in a table such as this, where we're checking these different factors: the slope, riprap size, riprap gradation, shape, density, thickness, extent of coverage, and launchable volume against those EM 1601 design standards. And this gives us the holistic perspective on whether or not an existing site is meeting current modern day design standards. As a summary of what we've conducted so far, we've assessed 43 sites for approximately 7.2 miles of existing revetment on the Lower American River and Sacramento River East Levee. The above water fieldwork delineated the riprap extents and types. We provided representative transects to measure riprap slope, gradation, shape, thickness, and density. And then the below water field work involved the multi-beam, side scan sonar, and sub-bottom data to provide lower bank and toe riprap coverage, elevations, and slopes. This allowed for a check against as-built info to determine if rock has launched and if the site meets the launchable rock volume requirements. The project is still ongoing, but preliminary results are showing that most sites are meeting the Army Corps of Engineers EM 1601 design standards, given the latest HEC-RAS 2D modeling and fieldwork data. So therefore, this methodology is creating a significant cost savings by reducing the total mileage of bank protection needed, which in turn reduces also the need for offsite mitigation. So that's the presentation that I have for today. Thank you for your time, and let me know if you have any questions.